Question 1. The production process is out of control when the proportion of defects is greater than or exceeds 3%. Now, the claim is that production is not out of control. What that means is that the proportion of defects is less than or equal to that 3%. So when we set up our hypotheses, our null and alternate hypothesis, the claim happens to be a null hypothesis. Notice that the proportion is less than or equal to 0.03. The complement is that the proportion is greater. We look at the alternate hypothesis and notice that this inequality is greater than. It's pointing to the right. So we have a right tail test. Our rejection region, we reject the null. This is a do not reject the null hypothesis. Now, the level of significance here, alpha, is 1%. This is our level of significance. This implies that this region here is 49%. So when we look for our critical value, we find it to be 2.325 while working backwards and using our z-table. This is our decision rule. Now the sample information gives us a sample size of 85 with a sample proportion of 5.9%. We are using the traditional method here. Sample proportion of 5.9%. Using our test statistic formula here, we're going to compute by taking the sample proportion, subtracting the true proportion, divided by the square root of the true proportion times its complement over the sample size. So we're going to plug in these values, and we're going to take the 5.9% minus the 3% over 0.03 times the complement, which is 97 or 0.97, divided by the square root of 85. Put the numerator in parentheses on your calculator so that we can enter this information efficiently. Divide by the square root of the 3% times its complement, which is 97%, divided by 85, close your parentheses. Now, since our critical value is to the nearest thousands, I guess we can say that our test statistic is approximately 1.567. This is our test statistic. To the nearest hundredths, it's about 1.57. Seeing where the test statistic lives on our decision rule, we'll notice that it lives somewhere over here. That's where our test statistic lives. It is to the left of our critical value of 2.325. So because of that, because the test statistic value of 1.567 is to the left of 2.325, it is clearly in the do not reject the null hypothesis region. So our conclusion is to simply not reject the null. We do not reject the null. What this sample has demonstrated is simply we are not rejecting the null hypothesis. The null hypothesis being that the proportion of defects is less than or equal to 0.03. In other words, we are validating the claim that production is not out of control. Question 3. Question 3 is making the claim that the percentage who will vote for the incumbent president is 53%. So the claim is that P is 53%. This will vote for the incumbent president, the true proportion. It turns out that this is a null hypothesis. So, the null hypothesis is that the proportion is 53%, and the alternate is that the proportion is simply not. Let's notice that we look again at the alternate hypothesis, and we have a not equal. This indicates we have a two-tail test. Decision rule for a two-tail test. Reject or null. And this is our do not reject the null region. We are having two critical values, since this is a two-tail test. Now, alpha here is 10%. So alpha being 10% means there's 5% in each tail. What that implies is this region here that's not shaded is 45%. So using our z-table and working backwards, we find critical values of 1.645. And because of symmetry, minus 1.645. This defines the rejection regions from the do not reject the null hypothesis regions. One region, do not reject the null. Two, reject the null hypothesis regions. Our sample information. We have a sample size of 100 and a sample proportion of 45%, which is 0.45. Using the test statistic, that's our sample proportion minus a true proportion, divided by the square root of the true proportion, each complement over the sample size. 0.45 minus 0.53. .53 times the complement 0.47 over the 100. Enter this on our calculator. Put parentheses around the numerator so we can tell the calculator that deduce the difference as the numerator, divide by the square root of 0.53 times 0.47 divided by 100. We get negative 1.60 if we approximate to the nearest hundredths. Now if we approximate this to the nearest thousandths, it is negative 0.1602. And if you like, we can approximate this to the nearest thousandths. Our test statistic is given to the nearest thousandths. So let's see where this value lives in our decision rule. Negative 1.602. The test statistic is negative, so it's to the left. But it's not quite negative 1.645. Negative 1.60 is pretty close. It is over here. This is where we can approximate the location of our test statistic. Notice that it is in the do not reject region. The test statistic of a negative 1.602 is not quite negative 1.645. It is in the do not reject or null hypothesis region. So our conclusion is do not reject the null. Do not reject the null. What that means is we have validated the claim, which is that 53% will vote for the incumbent president based on this sample. This sample shows that 53% will vote for the incumbent. Question 5. Question 5 makes the claim that "34% of American fathers take no responsibility for childcare." A researcher claims that the figure is higher. The figure is greater. So the proportion that take no responsibility that proportion is higher. It is greater than the 34% that is claimed in the article. So, our hypotheses, a null and an alternate. The claim happens to be an alternate hypothesis. So, the null is the opposite, which will be less than or equal. So we have a null hypothesis of less than or equal to 34%, an alternate hypothesis which is greater or exceeds 34%. Notice the alternate hypothesis. We have a right tail test since this is greater than and points to the right. Let's create our decision rule. Reject the null. Do not reject the null. We have a critical value. And in this question, the level of significance is 5%. So alpha is 5%. 5% is in our tail. That implies that this region is 45%. So working backwards in our z-table, we get a critical value of 1.645. The sample information tells us that we have a sample size of 234. There are 96 successes, which implies that we have a approximating this to the nearest hundredths, we got a 41% sample proportion. Our test statistic. .41 minus 0.34 square root of 0.34 times 0.66 over 234. Enter. And if we approximate this to the nearest hundredths, our test statistic is 2.26. Let's see where 2.26 lives on the decision rule. 2.26 is positive, so it's to the right of 0, and it certainly goes past our 1.645 critical value. 2.26 could be somewhere over here. Point being, our test statistic value lives past the critical value. It is in the rejection region. We will be rejecting the null hypothesis because of where the test statistic lives on our decision rule. We're going to reject the null. Now, rejecting the null hypothesis. Going back to our setup. This is rejected. So, the sample information verifies the claim that greater than 34% of American fathers take no responsibility for their children. Rejecting the null means accepting the alternate based on the sample that was taken. Question 7. Question 7 states more than half of those using the drug experience relief. It's a clinical study of an allergy drug. More than half experience relief. The claim, more than half. The proportion is greater than half, or 50%, which is 0.5. The null hypothesis and the alternate hypothesis are set up. So more than half experience relief. The claim happens to be an alternate hypothesis. So the null will be the opposite, which is less than or equal to 50%. This here, this proportion, greater than 50%. As a decimal is 0.5. So this is the claim made by the study. These people experience relief. Looking at the alternate hypothesis, yet again we have a right tail test. Drawing our rejection region. Reject the null. Do not reject the null. You need a critical value. Question 7 says use the 1% level of significance. So alpha here is 1%. That implies we have 49% in this region. So that means we have a critical value of 2.325. Let's look at our sample information. The sample information in this question tells us that 108 out of 202 subjects report experiencing significant relief. 108 out of 202. If we approximate this sample proportion to the nearest hundredths, we see this is about 53%. The test statistic will be sample proportion minus the true proportion divided by square root of the true proportion times its complement over the sample size. We get 0.53 minus 0.50 square root of 0.50 times its complement, which is 0.50, divided by 202. If we approximate the test statistic to the nearest hundredths, we get 0.85. This is our test statistic value. Let's see where this lives on the decision rule. 0.85 is positive. It is close to 0. It is not quite past our test statistic value of 2.325. It is somewhere over here, our test statistic. It is clearly in the do not reject the null hypothesis region. So our conclusion is to not reject the null. Now, not rejecting the null. In some sense means accepting the null. The sample information implies that the proportion that experience relief is certainly less than the 50%, less than or equal. What this shows is that the claim is not supported by the sample. The claim being more than 50% experience relief. Sobriety test. Test the claim that the true mean score for all sober subjects is equal to 35. So the claim for sobriety testing is that their score, their mean score, is equal to 35. The claim happens to be a null hypothesis, so the alternate will be not equal. The opposite of equal is not equal. This means, since we have a not equal for the alternate hypothesis, again, we look at the alternate hypothesis, we see a not equal. This means we have a two-tail test. This is our rejection regions. Two tails. Question 9, the level of significance is 1%. We are using the 1% level of significance. So, since we have two tails, alpha being 1%, 0.5% is in the right tail, while the other half is in the left tail. Now what that implies is we have here 49% in the do not reject the null hypothesis region. However, before we find our critical values, notice our sample taken here is small. Sample information, we got 19 data values. Excuse me, we have 20 data values that were collected. 20 data values gave us a sample mean of 41 with a sample standard deviation of 3.7. What this means, ladies and gentlemen, is since we have a small sample, we will be using our t-table. We need t alpha over 2 values for critical values. The t-table works by locating a degree of freedom row. Degree of freedom is 1 minus the sample size. So the sample size is 20. 20 minus 1 gives us 19. We will be looking for an alpha column. Since alpha is 1% and we have 2 tails, look for the 1% two-tail column with row 19 for its degree of freedom. What you find is 2.861 for a critical value. That's 2.861. This is from our t-table because we are taking a small sample. We found the t alpha over 2 values are critical values. 2.861, and this will be minus 2.861 for critical values. Now to compute the test statistic is the sample mean minus the true mean over the sample standard deviation divided by the square root of the sample size. So using the information of this problem, we get 41 minus 35 over 3.7 divided by the square root of 20. I would recommend for the denominator put parentheses. So you'll have 3.7 divided by the square root now of 20. What you're saying to the calculator is you have a numerator where there's subtraction, we do, a denominator that has a division problem, we do. Perform those operations before you do the division, right in the middle here. If you enter this information this way, we get our test statistic value very easily. If we approximate to the nearest hundredths, it's 7.25. This is our test statistic value. Let's see where 7.25 lives on the decision rule. As you can see, 7.25 is off the charts in some way. Any critical value that's between negative 2.861 and positive 2.861 is in this middle region here. 7.25 is pretty much way out here for a test statistic value. Now, as I said, this is somewhat off the charts. Any test statistic value that is greater than 2.861 lives in this right tail region known as a reject the null hypothesis region. So this value out here, very much past 2.861, implies we reject our null hypothesis as a conclusion. So we reject the null. In some sense, rejecting the null based on the sample information means that we accept the alternate. And that's just saying that based on this particular sample, the claim that the mean score is 35 is incorrect, is invalid. It is not supported by the sample. This is an invalid claim based on sample information. Question 11. Question 11 has a claim that convicted burglars spend an average of 18.7 months in jail. Claim. Convicted burglars. They spend a mean of 18.7 months in jail. Now the claim just happens to be a null hypothesis, that the mean here is 18.7. Now the opposite is that the mean is not 18.7. Looking at the alternate hypothesis, we notice that it's not equal, which means we have a two-tail test. Creating a two-tail decision rule for question 11, they tell us that alpha here is 5%. So we're going to have two critical values. However, sample information that is given to us in question 11, again, is a small sample. Sample size here is 11 with a sample mean of 21.3, sample standard deviation of 7.7. And again, we have a small sample. We will have to use the student's distribution, or the t-table here. Using the t-table, we need a degree of freedom. Remember, the degree of freedom is 1 minus the sample size. So in this question, 11 minus 1 gives us a degree of freedom equal to 10. So we will look for row 10. Alpha is 5%. And since we have a two-tail hypothesis test, we will look for 5% two tails. We see 2.228 in the 10th row, 5% two-tail column. 2.228. This is our critical value. We've now completed our decision rule. We need a test statistic. The test statistic is the sample mean minus the true mean divided by sample standard deviation divided by the square root of the sample size. Computing our test statistic, we get 21.3 minus 18.7 divided by 7.7 divided by the square root of 11. Let's enter this in our calculator. Remember, use parentheses for the numerator when you subtract the means, and then use a set for the denominator. Approximating this test statistic value to the nearest hundredths, the 9 says add 1 to the 1 and you get a 2. So it's 1.12 for a test statistic value. Let's see where this lives in our decision rule. 1.12. Well, notice, any test statistic that lives between our critical values of negative 2.228 and positive 2.228 would give us a do not reject the null hypothesis conclusion. Our test statistic is 1.12, which means it's around here somewhere for a test statistic value. It's not quite 2.228. In fact, it's about half, approximately. So it's halfway to the critical value. It's positive, so it's around here. Point being, it is clearly in the do not reject the null hypothesis region. Do not reject our null hypothesis. This is our conclusion. Do not reject the null. Do not reject the null in some sense means we accept the null. What that means is that the sample information, although it's small, verifies the claim that convicts of burglaries spend an average of 18.7 months in jail. The sample information supports the claim. Question 13. Question 13. A cereal company claims the mean weight of cereal in its packets is at least 14 ounces. So the claim serial weight has a mean that is at least greater than or equal to 14. And this is in ounces. We have a null and an alternate hypothesis. The null is greater than or equal to 14. The alternate is less than 14. Looking at the alternate hypothesis, we notice we have a left tail test. The inequality points to the left. It is less than. This is a reject the null hypothesis region. This is a do not reject the null hypothesis region. We need a critical value. Now, the sample information here that's given in the problem has a sample size of 8 values. We don't know yet what the sample mean is or the sample standard deviation. The point is we have a small sample. Because we have a small sample, when we create this decision rule, we need to use the student's distribution or the t-table to find our critical values. The level of significance is 1%. So alpha in this question is 1%. Using the t-table, again, we need a degree of freedom value. The degree of freedom is 8 minus 1 are 7. We're looking at the 7th row. 0.01 two-tail column. We find a critical value of 2.998. 1% two-tail, level of significance, 7th row, 2.998 critical value. So this will be minus 2.998 as a critical value. We have finished our decision rule. We now have to use our test statistic. But in order to use a test statistic, we have to get our sample mean and sample standard deviation from the list of data they gave us. In this problem, they're going to make us compute the sample mean and the sample standard deviation ourselves. So, the data that they gave us here, 14.6, 13.8, 14.1, 13.7, 14.0, 14.4, 13.6, 14.2 has a sum of 112.4. Square the data. Each one of these data values needs to be squared. We'll get a 213.16 if we square 14.6. We get a 190.44 if I square 13.8. 198.81, 187.69, 196, 207.36 by squaring 14.4. Squaring 13.6, we'll get 184.96. And squaring 14.2, we get 201.64. Adding these values gives us 1580.06. Now, computing the sample mean, it's the sum of the data divided by the sample size. So in this problem, we will take the sum of our data values, which is 112.4, and we'll divide by the sample size, which was 8. And we get a sample mean here that is 14.05 for a sample mean. This is our sample mean, 14.05. Now, computing the standard deviation is a little bit more tricky. Standard deviation is the square root of the variance. But computing the variance here, we will use the shortcut formula, which is n sum x squared minus sum x in parentheses over n times n minus 1. 8 times 1580.06 minus 112.4 squared divided by 8 times 7. This will give us a variance. Use parentheses here for the numerator again. 8 times 1580.06 minus 112.4 squared, close your parentheses, divided by 8 times 7. This will give us our variance. The variance here is 0.12. Now remember, the standard deviation is what we're looking for. Standard deviation is square root of variance. So, if we take the 0.12, the square root of 0.12 that is, use answer, which is 0.12, that's prior answer, we get this value. Notice square root 0.12 is what you see here. So if we approximate our standard deviation to be maybe the tenths, hundredths, thousandths, 10 thousandths, 0.3464, we get an accurate standard deviation. This is what we use for our test statistic value. .3464. We're now ready to compute our test statistic. Your test statistic is going to be, again, sample mean minus the true mean over sample standard deviation over the sample size, square root of the sample size, that is. So we'll get 14.05 minus 14 over 0.3464 divided by the square root of 8. Remember, use a set of parentheses for the numerator and a set of parentheses for the denominator. In the middle you have a division operation, which is what you see over here. If you hit enter, you get a test statistic value, and if we approximate to the nearest tenth hundredths, the 8 to the right says add 1 to 0, so the test statistic is 0.41. Let's see where this lives on our decision rule. .41 is positive and it's close to 0. So our test statistic here is about in that position. It's a little bit to the right of 0, but it's clearly in the do not reject the null hypothesis region. It's clearly there. So that's our conclusion. Do not reject the null. Do not reject the null. Let's go back. Do not reject the null. In some sense, the sample information is saying to us to accept that null. Do not reject it. The sample supports the claim of cereal weight exceeding or being at least 14 ounces. The sample supports our claim. That product recognition rates are the same in both states. Same rates. That is, New York versus California have the same recognition rates. That means that the proportions are equal. Population 1 will represent New York, while population 2 represents California. So that we have our null and alternate hypotheses. The null hypothesis is the equal proportion, so the claim happens to be a null, and the alternate hypothesis is not equal. Again, population 1 represents New York, while population 2 represents California. However, these P's are proportions. So proportion 1 equals proportion 2 for the individual populations. P does not stand for population here, it's proportion. Now, since our alternate hypothesis, when we look at this, is a not equal, This is a two-tailed test. So we're going to construct our decision rule here, a two-tailed decision rule. This is reject the null. Do not reject the null. Now alpha here in question 15 is 5%. This is a 5% level of significance. What that implies is, if this is 5%, that's half of 5%, which means it's 2.5%. 2.5% is in each tail. 95% is in the middle, or simply 47.5% is in this important region here. What that means is, by using our z-table and working backwards, we look for 47.5%, or a critical value of 1.96, and a minus 1.96 critical value. So any critical scores between negative 1.96 and positive 1.96 is a do not reject the null hypothesis. Now, sample information. We have two populations, population 1 and population 2. New York is population 1, while California is population 2. The sample proportion for population 1 indicates that of 558 New York surveyed, 193 knew the product. So, sample proportion 1, which represents population 1, New York, will be 193 over 558. Sample proportion 2 gives us 196 over 614. This is for California. So using our calculator, we're going to compute these proportions. $193 divided by 558 gives us, if we approximate to the nearest thousandths, 0.34. 5 is in the thousandths position. Look at the digit to the right. It's an 8. Add 1. Sample proportion 1 is approximately 0.346. You can say it's approximate. While sample proportion 2 196 divided by 614. If we approximate this to the nearest thousandths, we get 0.319. Now, the thing about this is we also need what's known as a pooled proportion. That's when we pool our resources, put them together. The definition is the sum of the successes over the sum of the sample sizes for each population, the New York and the California. So here we'll get 193 plus 196 for the successes over 558 plus 614. Let's put this in parentheses here, a sum, 193 plus 196 divided by 558 plus 614. If we approximate this to the nearest thousandths, the pooled proportion is 0.332. The 9 says add 1 to the 1 and you get 0.332. Now, we're going to use all of this information here. Sample proportion 1, sample proportion 2, and the pooled proportion. I know your book uses P with this symbol here. Looks like a caret symbol on top of the P for pooled proportion. I will be using the squiggle for pooled proportion. Now I want to note that the complement of the pooled proportion, which is important, 1 minus 0.332 is 0.668. This is the complement. So, the complement of the pooled proportion, 0.668, will be used as well because our test statistic formula is the following. It is the difference of sample proportions. The pooled proportion times its complement over the sample size of population 1 plus the pooled proportion times its complement over the sample size of population 2. This is why I pointed out we need the complement of our pooled proportion. So, entering this in our calculator, let's write this down. .346 minus 0.668. Now, 0.332 times we made a mistake. The second sample proportion is 0.319. Okay. Sample proportion 1 minus sample proportion 2. Now we have our pooled proportion times its complement, 0.332 times 0.668, divided by sample size 1 of 558, plus 0.332 times 0.668, divided by 614. Enter this information in your calculator. Now be careful here. Automatically when you use square root, let's go back, we got to divide by a square root. I'm going to suggest you put a second open parentheses. So you have a parentheses within a parentheses. Within that first set, or I should say, the first parentheses just says whatever comes next is under the square root. Now, I have a couple of things coming. I'm going to put 0.332 times 0.668 divided by 558. Close the parentheses. I'm communicating to the calculator that I have a product and a quotient under the radical that I want to add to another product and quotient, so I'm going to have to enter another open parentheses. So we have nested parentheses here. This big parentheses that's outside of the arithmetic, under the radical here, is just saying all of this is under the square root. We now have the components. This first information plus second information. So it's 0.332 again times 0.668 divided by the second sample size, which is 614. Close your parentheses. Now close the parentheses to indicate to the calculator we have two closed parentheses here. The second one, or the last one, is simply saying everything between the first open and the last closed is under the radical, which is true. This is what you want to communicate to your calculator so that when you hit enter, you get the value you need for your test statistic. And if we approximate this test statistic to the nearest hundredths, we find that it's 0.98. .98 for a test statistic value. Let's see where this lives on our decision rule. Now 0.98 is positive, and it's not quite 1. But notice if the critical value is 1.96, 0.98 as a test statistic would be halfway. This is where the test statistic would live. Notice it's clearly in the do not reject the null hypothesis region. This is our conclusion. Do not reject the null. So if our conclusion is to do not reject the null hypothesis, let's stop and think about what this means. We do not reject this. This happens to be the claim that's made. So what that means is that the sample information supports the claim being made that the recognition rates truly are the same. They have the same recognition rates. Question 17. Religious service. Test the claim that the two proportions are equal. So we're also testing here in question 17, we have what's known as equal proportions. We have equal proportions. Okay? I guess those that attend service at least once a week versus those who do not attend service at least once a month. Equal proportions. Now let's take a look here. The first group, question 17, these are the ones who attend at least once a week. So I'm going to put down and notate attend at least once a week. Now this is going to be compared to who attend at least once a month. Okay. two groups. Group 1, Group 2. Population 1, Population 2. They're claiming that the rates are the same. So, let's take a look at this. P1 is the same as P2. We set up our hypotheses. P1 equals P2 is a null. P1 not equal to P2 is the alternate. Yet again, we are looking at the alternate hypothesis. I put my eyeball there to demonstrate that we have a do not equal here for the alternate, which means we have a two-tailed test. Let's create our decision rule. Two tails. Rejection region. This is a do not reject the null region. Question 17 has a 5% level of significance. Alpha is 5%, which means 2.5% is on the right tail, 2.5 is on the left tail, and that implies that this will be 50 minus 2.5, or 47.5%. Now, looking back at our z-table, working backwards, we have a critical value of 1.96 to the right and a negative 1.96 to the left. These are my critical values. We now have our sample information. Sample information says for population 1, the sample proportion was 31 out of 1,000, while the sample proportion for the second group was 22 out of 1,200. Let's see what this gives us. Sample proportion 1, 31 divided by 1,000 is 0.031. Sample proportion 2 gives us 22 divided by 1,200. Now, we're going to approximate this to the thousands. So this will be 0.018. We now have to enter our pooled proportion. Pooled proportion. The sum of the successes, 31 plus 22, divided by the sum of the sample sizes, 1,000 plus 1,200. Now if we approximate this to the nearest thousandths, 4 is in the thousandths, this is approximately 0.024. Or 2.4%. Now notice we need the complement of 0.024 because we're going to use this in our test statistic value, and it's 0.976. So let's notate this. The complement of the pooled proportion is 0.976. We're going to use all this information. Now again, the test statistic is sample proportion 1 minus sample proportion 2. Pool proportion times its complement over sample size 1. Pool proportion times its complement over sample size 2. .031 minus 0.018. 0.024 times 0.976 over 1,000 plus 0.024 times 0.976 over 1,200. Let's enter this carefully in our calculator again. Use parentheses for the numerator, divide by square root. Be very careful. Under this radical, we have some information. We have a product, a quotient here, and a sum of another product and quotient. So for each product and quotient, I will put an open parentheses and a closed parentheses. 0.024 times 0.976 divided by 1,000, close a parentheses, plus open parentheses 0.024 times 0.976 divided this time by 1,200. Close your parentheses. Now we need to close the parentheses again one final time to communicate to the calculator that everything between the original open parentheses and this last closed parentheses is under your radical, which it is. You can now hit enter. Now if we approximate this to the nearest hundredths, we get the 3 in the thousandths, so this will be approximately 0.198, no change to the 8. .198 is our test statistic value. Let's see where this lives on the decision rule. Sorry, that's 1.98. Okay. 1.98 as a test statistic. Wow, let's take a look. It's 1.98, which is to the right of 0. It's positive. Now, it's past 1.96. It's past 1.96, so 1.98 is over here somewhere as a test statistic. It is slightly past the critical value, which indicates that it's actually in a rejection region. We are rejecting the null hypothesis based on this sample because the test statistic is 1.98. It is to the right of our critical value. We will reject the null. Now, rejecting the null means in some sense accepting the alternate. What this means is that, based on sample information, the claim made is not valid. The sample does not support the original claim that the rates are equal. What the sample suggests is that they're not equal. Question 19. Again, in a random sample, 5 in a random sample of 450 people, 25 of 29, 14 were smokers. So, test the claim that the proportion of the smokers in the two age groups are the same. So again, the claim is about smoking with two independent age groups. They're making the claim that the proportion or the rates are the same for each group. The proportions are equal. Group 1 represents 20 to 24-year-olds, while Group 2 represents 25 to 29-year-olds. Do they smoke at the same rate? We have a null hypothesis and an alternate hypothesis. The claim that's made happens to be a null hypothesis, so we'll set them equal, while the opposite is not equal. What this means again is we have a not equal for an alternate hypothesis. This is a two-tailed test. Creating our decision rule. We're going to reject the null. We're going to do not reject the null. Now alpha here is 1%, which implies that 49% is this non-shaded region. 99% is this non-shaded region, which means 49.5% is this right portion of the non-shaded region. That's important because when we work backwards using our z-table, we find a critical value of 2.575. And a second critical value of minus 2.575. So let's take a look at our sample information. Our sample information says that the sample size for group 1 is 500, while the sample proportion for group 1 they compute as being 0.22, or 22%. For group 2, the sample size is 450, and they compute a sample proportion being 14%, or 0.14. Now, we have to notice that we're going to use the sample proportions in our test statistic formula. But let's note that in order to compute a pooled proportion, we need the number of successes. So, the number of successes of group 1 is found by taking the rate of 0.22, or 22%, and multiplying it by 500. So, 0.22 times 500 gives us 110. In group 1, there was 110 successes. In group 2, the number of successes is the rate of 14% times 450. We get 63. So there are 63 successes. Our pooled proportion, the sum of the successes of 110 plus 63, divided by the sum of the sample sizes, 500 plus 450. This will give us our pooled proportion. We get a pooled proportion approximated to the nearest thousandths of 0.182, or 18.2%. We're going to use this. Note, the complement will be the complement of 0.182, 1 minus 0.182, thinking ahead here, is 0.818. We're going to use this information as well. So, combined with the two sample proportions, 22 and 14, we can now compute our test statistic. Test statistic will be difference of sample proportions divided by, again, pooled proportion times its complement over sample size 1, pooled proportion times its complement divided by sample size 2. Let's see what we get. Let's use our calculator. Don't forget to close this with a second close parenthesis. Again, everything between the first parentheses and the last is under our square root. Let's hit enter. We get a test statistic approximated to the nearest hundredths of being 3.19. .19 is our approximate test statistic value. Let's see where this lives on our decision rule. 3.19 is positive and it is past the 2.575 critical value. It's somewhere over here. It is clearly in our reject the null hypothesis region. We are going to reject the null. Now, rejecting the null in some sense means accepting the alternate. All this is saying is based on the sample information, the claim that the rates are the same is not supported. And finally, question 21. Question 21, we have two types of flares that are tested for their burning times in minutes with given sample information. Claim that the populations have equal means. So the claim is we have two products brand X versus brand Y, and I guess they represent some sort of burning times. Both brands are two types of flares. So they're trying to say that they both have a mean burning time rate that is equal, that the brands have the same rate. We're going to test this claim. Now, brand X represents mean 1, or brand X has a mean, we'll call for group or population 1. Brand Y is our second group, our second population, and it has its mean. Equal, not equal. These are opposites. Again, we look at the alternate hypothesis and see a not equal. This means we have a two-tailed problem with a not equal. Our decision rule will be two tails. Now the level of significance in this problem, they tell us, is 5%. So if this is 5%, we have 2.5 in each tail. Or we can think that the non-shaded region is 95%. It's the complement of 5%. Half of 95 is 47.5%. That's important in deducing our critical values, and when we work backwards looking at our z-table, we find critical values of 1.96 and minus 1.96. Now, sample information. We have two groups again, brand X and our versus brand Y. Sample 1 of size 35 gives us a sample mean of 19.4 with a sample standard deviation being 1.4. Brand Y has a sample size of 40 with a sample mean being 15.1 In a sample, this is the second group, not the first. And a sample standard deviation of size or of value 0.8. This is the sample information. We're now ready to compute our test statistic. The test statistic is found by taking the difference of two sample means divided by the square root of sample variance for group 1, the sample size of group 1 or population 1, sample variance from sample 2 over the sample size of sample 2. Let's see what we get. $19.4 minus $15.1. 1.4 squared over 35 plus 0.8 squared over 40. Let's enter this in our calculator. Parentheses 19.4 minus 15.1. Close the parentheses, divided by square root. Now we have another set of work to do. 1.4 squared divided by 35. Close your parentheses, add 0.8 squared divided by 40. Close your parentheses. Make sure you have a second close parentheses to tell your calculator that we're through entering information that is under the radical. Hit enter. Now if we approximate this to the nearest thousandths, we get 16.025 for a test statistic. Let's see where this lives on our decision rule. $16.025 looks like it's way off the charts somewhere over here as a test statistic value. It is very much past the critical value of 1.96. It is positive and it's very much past that value. It's at 16.025. It is very much in the reject the null hypothesis region. So our conclusion here would be to reject the null. We will reject the null hypothesis as a conclusion. Now rejecting the null in some sense says we accept the alternate, but what this really means is that the sample does not support the claim that the means are the same. What this sample suggests is that the means are not the same.